Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Get started. This is actually our third annual workshop on advances in quantum algorithms and devices. I'm very excited that we have this yet again, and we have lots of wonderful speakers lined up this morning and this afternoon. So thank you all for coming again to the Faculty Summit and to our workshop. We always love this week in July when everyone's here. It's a lot of excitement. So it's great to see some faces back again and some new faces this year. Just a couple of notes. We'll have 2 coffee breaks. We'll have a lunch. The lunch will be out where we had breakfast this morning. When we do have questions, if you could please use this mic to ask the question. That's really for, I know we can all hear each other, but for recording purposes, we'll ask that you use the mic so that for later, after the fact, people can also hear the question. So I think we'll just jump in and get started.
Okay.
Our first speaker is Rod Van Meter, and he's going to talk to us about distributed density matrices.
Yeah, thank you. Burton, you can't see, can you? I just noticed what.
Well, no.
Can you? Let's move this over a little bit anyway.
All right.
So it's customary for speakers to start by thanking the organizers, and I always hate that because during that 15 seconds you're thanking the organizers, people start to check their mail and never come back and pay attention to you. But since I am the first speaker at the last day of things, and Microsoft has been so generous, and Krista in particular has been great about getting this whole thing organized. I really want to thank Krista and the other Microsoft folks here for all they're doing, and say congratulations on the kind of visibility you're getting, as we saw in the talks by Harry Shum and Peter Lee, mentioning explicitly the work that you guys are doing. I think it's great, and I'm thrilled that Microsoft is doing so much interesting work on things and sees so much future in this field we're working in. So I'm a professor at Keio University in Japan, and I call my research group AQUA for Advancing Quantum Architecture. So we have a couple of water-related pictures there for you. Today I'm going to talk about distributed density matrix management. And over the last 2.5 days, starting from dinner on Tuesday night, every time I've had a conversation, the amount of things I wanted to put into this talk has actually grown. So I'm going to try to blast through some stuff early on in this talk where I'm just going to mention some chunks of work that we've been doing, and if you actually want to discuss those, come find me later at any of the breaks during the day, and we'll actually talk about them. And then hopefully I'll spend most of this time actually presenting a problem definition. I can't say I have a full answer to this particular problem yet, but I want to convince you that there's an interesting problem here that actually needs to be solved, and propose several possible solutions, none of which really make me happy. Let's see. So as I said, my group is Advancing Quantum Architecture. And the overall area in which we are working is distributed quantum computing architectures, including some work on devices, which we've mostly discontinued. That was with Yoshi Yamamoto's group at Stanford. Some work on workloads, which figured into my PhD thesis the better part of a decade ago at this point. Some principles and tools, and the thing that ties it all together is networks, and that's really what I'm going to be talking about today, is networks. But I realized, this slide I made a long time ago now, but I've realized actually that a lot of the work we've done in the last several years has been about how to actually implement quantum error correction efficiently. We're not really working on the theory of error correction, but we're working on figuring out what the constraints are on machines to actually run it efficiently, and in particular focusing mostly on the surface code. Let's see. So just to blast through some of the stuff we've done recently, some of you all have seen the work on Solovey-Kitaev. The first author of this was actually this is a Phys Rev paper. The first author was an undergrad of mine. And recently we've done some work on design for a floating point adder, which was also done by an undergrad of mine. And a paper of mine on quantum computing's classical problem and classical computing quantum problem. And about 2 years ago now, we had an article appear in Communications of the ACM that actually made the cover on a blueprint for building a quantum computer, which sounds a little bit like, I thought that was sort of a grandiose title, but was actually suggested to us by one of the reviewers. So I was happy to adopt it and go. And for those of you, a couple of you all have asked, since I live in Japan, so do you read and write Japanese, and do you actually publish stuff in Japanese? Yes, last year I published my first paper actually in Japanese. And after I wrote the first draft and gave it to my co-authors, they came back to me and said, we have no idea what you're talking about. So my empathy for non-native English speakers writing research papers in English went way up during the process of writing this paper. I can tell you that. It was already high, though. So today we're actually going to talk about quantum networking, which is an area that I published a book in last year. There's a copy somewhere between, that's, I guess, in some sort of superposition state between Martin's office and Dave's office at this point. Did you find it? OK, good. But I think Microsoft should buy more copies, personally. So in networks, we're talking primarily about quantum repeater networks where the goal is to create shared entanglement end-to-end that we're going to use for some purpose or another. I divide the set of things that you might like to do with such a quantum network into essentially 3 areas. One of which is distributed cryptographic functions. One is sort of cybernetic operations where you're talking about physical interaction of the quantum state with the environment in some way. You can call those all sort of sensor operations. And then there's just plain digital distributed computation. There are a number of things that have been proposed in this area. I have a student right now who's actually looking at quantum Byzantine agreement. There's leader election. Quantum key distribution, which is probably the single most famous set of things up here, falls sort of on that boundary between sensor networks and distributed crypto function, because in fact what it's doing is it's testing the environment for the presence or absence of an eavesdropper. Some other sensor things, including some interferometry and clock synchronization and the like. And blind quantum computation is actually one of my very favorite things these days. If you don't know much about blind computation, I would encourage you to take a look at it. These things up here in the upper circle are attractive to people in the systems world because they reduce our dependency on computational complexity and one-way functions and public key cryptography and things of that nature. I do have to always sort of encourage the physicists to be careful about saying, but it gives us perfect secrecy, because I'm a systems person, and systems people all know that perfect secrecy doesn't exist in the real world. So this set of overall functions and whatnot, the crypto functions are largely what I would call low bandwidth operations. The sensor networks are high to very high bandwidth, and again, also the distributed computation, it turns out, is also high to very high bandwidth, where this is sort of the low bandwidth stuff you could make do with creating entangled states between end nodes at tens of qubits per second, whereas for some of these functions down and through here, you might need as much as 10 to the 11 bell pairs per second in a network, which is a very large number. Any questions on this stuff before I move on? This is just sort of setting the stage here. Anything? Let's go. In networking stuff, we have also published a recent set of things, path selection for quantum repeater networks, how you choose a path through a network, fault-tolerant operations for blind quantum computation, classification of attacks on the quantum repeater network itself, and one that we're just about to get accepted, I hope, how to actually do high-speed quantum networking using a container ship. Literally, physically a container ship, the kind of thing that moves your Nikes back and forth between here and China. Ask me about any of these things later if you want. A couple of things that we are working on right now. Heterogeneously encoded bell pairs. So take a bell pair, a physical bell pair, split it apart, and take one of the component members of the bell pair and encode it in the Steen code, and one of the bell pairs and encode it in something like the surface code. And we can use this for quantum internetworking between nodes or types of networks. This work and the next one that I'm going to talk about real quick were done by a few of my undergrad or a few of my students. Kaori on the right, she's now working for as a programmer for a gaming company. The other two are about to finish their PhDs, one with me and one at the University of Tokyo. And the basic result of this, we're still in the process of visualizing this. This data is only a few days old. We still need quite a bit of work on this. But the basic result we've come out with so far is that if you want to do this, that it seems like the right scheme is actually going to be to take those physical bell pairs, do the encoding into error correction schemes, and then take sets of those and do purification on top of the logically encoded qubits. Seems to give us the best sort of output rate and the best use of resources. Another one, Martin was asking me about network coding stuff the other day when Martin and I got to have a talk. How many of you all here are familiar with the basic concept of network coding, either classical or quantum? Only a few. Okay, so the basic idea is you've got this graph that you can use for communications, and what you would like to do is you would like to communicate between the upper left and the lower right and the upper right and the lower left, but there are resource conflicts on this. You can't do it in one single use of those set of links unless you act intelligently in some way or another. This is a well-known classical result. It has moved into the quantum domain in the last few years. And my former student, Sato, who is finishing his PhD at the University of Tokyo, worked out how to actually do this with quantum repeaters and how to actually get this to work. But still, all of that work was done with pure states. And in the last year or so, Kaori, my master's student, she has extended this to actually work with mixed states. And Sato is now finishing up a paper on this in the process. And that allows us to determine if you had an error on this bell pair and an error on that bell pair, what would sort of the end result be? Which of the sets of output states would actually have an error in them? In this particular configuration, it would be this bell pair winds up with an error in it, but not the other bell pair. Found some interesting things out of that. All right. That's sort of everything in 10 minutes. That's most of what my group has done in the last 3 or 4 years. If you want to talk about any of that, please come find me afterwards. Let's talk about distributed density matrix management, which is what I want to spend most of the rest of this time talking about. What exactly is a density matrix? Anybody care to venture an opinion on what a density matrix actually is?
Do you want us to give you a consistent interpretation of the quantum state? Or we could be here for a while.
We could be here for a while, right? This one actually, I've been out giving this talk off and on for the last year. And every time I go someplace and give this talk, actually most of the time I've done it with a whiteboard rather than with slides. But every time I've given this talk, it's gone differently. Because the audience seems to come to this with different preconceptions of what they're expecting or what they understand from the system as a whole. So sometimes we get stuck on this slide and spend 20 minutes, or on this topic and spend 20 minutes on this. Of course, mathematically, we all know this is the way you write it down. It's a statistical construct that represents our understanding of the state, right? Write out the numbers. It may look something like that. Or it may look something like this, which is, this is the written in the Bell basis. This is actually what comes out of some experiments from Rempe's group in the last couple of years. Right? So what is it, though? We're used to writing this symbol rho and maybe some numbers, but you don't really think about what it really is. Okay? What is it? What is a density matrix? Well, if you were going to actually calculate this density matrix, it actually exists as a data structure in memory of some machine or another, somewhere, right? Where that machine might actually be a graduate student with a pen and a piece of paper, but it exists in the memory of a machine somewhere. What we are worried about is not the size of the problem, which is sort of automatically one of the things you think about when you're thinking about quantum states. But we're dealing primarily here with 2-qubit states, Bell states, and so the size of the matrices themselves is not large. We're talking about 4 by 4 matrices, 16 complex numbers, it's 256 bytes, right? No big deal. The problem is not the size of it. The problem is being able to use these in a timely and consistent fashion. Okay? Nathan's giving me a puzzled look. Comments? Questions?
Well,
where's the mic?
Well, first off, what's the problem? Because it sounds like you're talking about software simulations of quantum systems rather than taking a look at quantum systems. So I'm just trying to understand what it is, what's the problem, and what are you addressing?
We're going to get there momentarily.
Okay.
I am interested in operational behavior of quantum repeater networks. So in the real world, when we start deploying quantum repeater networks that span the planet, how are these going to behave? How are we going to drive them? How are we going to make decisions inside of these systems? Now, the way you actually get this, the way you actually create this object of the density matrix, you've got some sort of experimental apparatus that's controlled by some sort of hard real-time system that creates an entangled belt pair of some sort. Out of this, you run some experiments, you collect a bunch of data. At this point, it's just raw data. This is all sort of soft real-time control of your experiment. And then sometime later, your graduate student, Alice, she comes along, after dinner and hanging out with the other students and whatnot. Oh, wait. But I've been told that Eddie Farty doesn't actually like Alice. So we'll put Alice in the witness protection program. I had dinner with Dave Bacon the other night, and he said that when he gave a talk in front of you one time, you said, that's the only time I've ever liked a talk that involved Alice and Bob. So. Yeah. All right. At any rate, so Alice comes along, and her job, or our anonymous graduate student comes along, and her job is actually to process this raw data into this density matrix, which exists now in the memory of her laptop. Right? Sometime divorced in some physical place, divorced from the actual experimental apparatus itself. All this is fine if your goal is this. Your goal is to create a nature paper. Right? You don't care when the density matrix gets calculated as long as it looks nice enough to appear in nature. But if the goal is, if our state is actually distributed, the control of the system must be as well. This gentleman is named Bob. He's a television personality in Japan. But Alice has her own device, and Bob has his own device. And this distance may actually be kilometers, tens of kilometers. And their relative understanding of what's going on can be out of date by that distance divided by the speed of light. Okay. Now, if we are planning on using this for real operational work in repeaters, those distances are significant. Particularly if we want to do this all the way between Tokyo and Seattle. What's the round trip between Tokyo and Seattle? Round trip time.
3 megameters.
3 megameters. Well, let's see, it's about 100 milliseconds, right? So it's actually 10 to, let's see, 3 to, it's about 100 milliseconds, so whatever that is.
10th of a second, so it's 3 times 10 to the 7th meters.
Nope, actually, because we're doing this in optical fiber, it's 2, right? So it's about 2/3 of this. As a complete aside, by the way, the people I work with are internet people, and they're perpetually worried about wanting to create a lower latency internet between places. And my answer is, rather than trying to reroute things, what they just need is they need faster light. The problem is that in fiber, you're only getting 70% of the speed of light. You could do this in other media and potentially get quite a bit of savings out of it. Anyway, that's an entirely different talk. Something like that. What we want is we want to make real-time use of this density matrix to actually control our set of operations. And here the argument broke down one time when I was giving this talk, because one of the physicists in the room objected and said, well, but the density matrix is just a statistical construct. You can never use it to talk about an individual state. You can only use it to talk about a large collection of states, a large ensemble. Right? I'm going to build a network. I'm going to have to figure out how to control it. Some of that control is going to be statistical. We're going to have to use these density matrices for this stuff. Nathan's, Al, yes.
What's your definition of real time? Rod, what's your definition of real time?
Slightly faster than that. Right? Well, that's going to depend on a number of elements of the behavior of the repeater itself. If you're dealing with any memory that decays, then real time means fast enough so that you can deal with that decoherence in some way, shape, or form. So some of the technologies we know, the flux qubits and the like, they're finally getting up close to a millisecond. Others are longer. But you need to be much faster than that. Moreover, since the number of memories we're talking about in each of these individual nodes is still relatively small, and you are waiting on acknowledgement messages as to whether or not things like entanglement succeeded, you need to deal with that at sort of round-trip latency time levels, and you would like to be able to do some of that stuff faster. So this is relatively hard real-time stuff. For some of these operations, actually the guy that I was working with while I was at Duke, Jung-Sang Kim, believes that the single biggest hurdle to actually making repeaters physically work is the need to distribute a very high precision clock between the nodes, where very high precision is 10 to the minus 12 or something like that. I think I'm going to trust the experimentalists to solve that problem. And at the systems level, what I care about is primarily going to be on the order of microseconds. Nathan, did you want to kick something in there? You started to say something too.
Oh, no, I was just smiling about Bayesianism versus frequentism.
Never
Never mind.
mind. Never mind. Different discussion. So what we are doing is we are depending on the predictive power of the density matrix to represent probable outcomes for individual quantum states. Individual ones. Because we're dealing operationally with one state at a time. So how many of you all are familiar with the operation of repeaters? A few, OK. Basic idea. We're going to show you sort of the basic idea here. 3 stations, 2 links. Each of those arrows is a qubit. First thing you have to do is you have to create entanglement between the two of them. And forgive my fabulous PowerPoint artistry. What we want to do is we actually want to create entanglement that spans this whole distance from station 0 to station 2, or however many hops we're dealing with. The way you do that is by doing what's called a Bell state measurement in the middle, and then communicating the classical results out. When you have done that, once this operation has completed, you now have entanglement that spans this distance. This is called entanglement swapping. It causes a decline in the fidelity of your end-to-end state. So what we must do afterwards is purification. And in the purification operation, you take 2 or sometimes more bell pairs that cover the same distance, that span the same pair of nodes. And we are going to use one of those bell pairs to test a proposition about the other bell pair. And if the test succeeds, then our confidence in the state of that bell pair increases. So what you do, local operations at both ends, measure out those qubits at both ends. You lose that entanglement there. And when it succeeds, you are left with higher fidelity entanglement. So the basic process of creating the entanglement swapping, and the purification are the 3 operations you need to actually build repeater networks. Yeah. Let's see. The way you get to longer distances, if you want to go from Tokyo to Seattle or someplace, you begin with the initial procedure proposed by Wolfgang Dürr and Hans Briegel is what they call nested entanglement swapping, and you can do this a stage at a time. You take your 4 one-hop bell pairs and turn it into 2 two-hop bell pairs, And then from there, do entanglement swapping again, and you get to one 4-hop bell pair. And you can repeat this process. So here's our conceptual hardware again. As I mentioned earlier, the distances we're talking about here are on the order of tens of microseconds or tens of kilometers. And we are going to need some sort of control mechanism at each of these nodes. And each one will wind up with a copy of a density matrix that represents, for each one of these quantum states that it's actually sharing with someone else. For repeaters, we're only doing this for bell pairs, and so we only need to worry about 2 nodes at a time for any of this stuff. So from this point forward, we're only going to deal with 2 or in one case 3 nodes in doing this. Okay, so what's so hard about this? I've been talking for 25 minutes already. I've got about 15 minutes left to go. We're just now getting to the problem. Right? What's hard about this? Well, in the laboratory, there are 4 simplifications that you don't get to use in a real-world operational network. One of these I already mentioned earlier. Graduate students creating density matrices, days after the experiment is actually run. Can't use that for operational work. These systems often operate with a single integrated controller, but we're going to wind up with controllers that are distributed across physical distances. Generally, the experiments being run today deal with a fixed sequence of operations. They're not making real-time decisions about what operation to actually conduct next. Third point. Fourth point, this is generally a well-known, well-characterized apparatus that everyone is using. In fact, you spend a lot of time tuning it and tracking it. None of these hold for operational repeater networks in the real world. This is why it starts to get hard. Okay. Let's go through a couple of these. Let's go through an example here. And operationally, what happens is that Alice and Bob and Eddie are all going to have a set of rules that they operate by, that they will decide whether it's time to do purification or whether it's time to do entanglement swapping. Okay. So what do those rules look like? Alice and Eddie's rules may look something like this. If I have 2 bell pairs with Bob of fidelity less than 0.98, then I'm going to run purification. If I have 1 bell pair with Eddie, let's see, and that's fidelity is above 0.98, then we're ready to actually use it for some sort of application purpose. That's another rule you might have. Eddie's rules would be similar and symmetric to that. Bob's rules are slightly different. If I have 2 bell pairs with Alice, then we're going to purify. But if I have 1 bell pair with Alice and 1 bell pair with Eddie, and they are both high enough fidelity, then we're going to do entanglement swapping. Okay. Fair enough? Now, what you would hope is that this decision to purify, that if Eddie decides to purify, that Alice is also going to decide to purify. What happens if Alice fires this rule, the choice to purify, and Eddie fires the rule to do entanglement swapping? Well, what you're going to wind up with, how could this actually happen? So we get entanglement here. Then the next thing that happens is Eddie and Bob succeed in creating entanglement there. Bob decides he's going to do entanglement swapping. Moments later, Alice succeeds in getting notification of the existence of a second bell pair, but perhaps due to some timing constraint or to some difference in their opinion about the behavior of the system itself, Alice believes not that the fidelity is 0.98. She believes it's 0.97, and she decides to purify. You're going to wind up with a state that looks like that. It's going to be a 3-qubit entangled state instead of the bell pair you want. This is junked. Right? So Burton.
It seems pretty crucial. The density matrix formulation would like agreement about what the density matrix looks like. You'd like to have these parties agree to what it looks like.
That's exactly what
And
we're
they
working
won't, I mean, in general, unless you do something pretty radical. But it occurs to me that that itself is a communication problem.
Mm-hmm.
So there's a sort of a bootstrapping of information issue here.
Yeah. So the very first time my collaborator, Shigeo Suzuki, who's working with me on this, the very first time he and I gave this talk, he actually gave the talk itself. And it was at Stanford in the lab of Yoshi Yamamoto, and we had students from Yelena Vukovic's group, and Hideo Mabuchi was there and on some of his group. And Shigeo's talking, and most of the people in the room are just going. And Hideo Mabuchi looks at it and he says, well, isn't this just a distributed database synchronization problem? Yes, Hideo gets it, right? He was the first person in the room to sort of understand what was going on. But for other people, some people will say, well, this is obvious, right? Others will say, I don't get what the problem is. It sort of varies. The goal, though, is to create this shared understanding of what this density matrix is going to be in a way that allows you to make these consistent decisions, ideally without having to pay round-trip communication costs between the nodes. Because those round-trip communication costs between the nodes cost you performance, and if your memory decoherence processes are significant, they may in fact make it impossible to actually operate correctly. If you're talking about latency of 100 milliseconds between Tokyo and Seattle, right, it's not going to happen. So what we need to do is we need to guarantee a consistent view of both the condition of the bell pairs and the set of bell pairs that we are actually operating on. All the decisions must be made under those conditions. So why is this hard? And I'm starting to run a little short on time here already. Here's a map of the internet in 1999. People have pretty much given up on drawing maps like this at this point. Beautiful map. Each one of those nodes in this map is not actually a node in the network. Each one of the nodes in this map is actually an entire network in its own right, which might look like that, or might look like that, or might look like that. So the network itself is extraordinarily complex. Okay. It also spans extraordinary distances. Okay. And in the process of doing this, in order to create a connection, you are going to wind up having to choose a path through this network of some sort. And in fact, it's going to wind up being largely a path of strangers. Okay. So Krista decides that she wants to connect to Matthias. Okay. How is she going to succeed in doing this? We're going to run through New York and Boston. Okay. But Krista's never met any of these people in the middle. So how do Krista and Matthias decide how we're actually going to do this communication? What is the structure of the network? What's the memory lifetime of things? Right, there are a whole bunch of unknowns. Who's involved? What the fidelity of local gates is? What the decoherence processes at each of these nodes are? Possibly, the repeaters that are operating here may decide, oh, I'm probably going to have to keep this qubit for a long time, but my physical error rate process, my physical decoherence is too high, so I'm going to encode it in an error correcting scheme. And like I talked about right at the beginning with the heterogeneous entangled bell pairs that we were talking about, that encoding process is itself a noisy process. And so after you've done it, you can then keep a qubit for a longer time, but you're paying a penalty for doing it. So you need to exchange information about that penalty. You need to be able to describe that to each other. Even things like how many memories there are that are available. So the key principles for actually getting this done, Alice and Bob, or everyone in the chain, must agree on the state that's actually being created. So what are we actually creating? That includes not just the desired state, but also the noise terms, and not just the fidelity, because actually the shape of the density matrix, where your off-diagonal terms are and what those are, affect the success of the purification process as well. They must agree on the creation time, because otherwise, if you're talking about decoherence processes, it's impossible to talk about them unless you know how long the state itself has been sitting around. and they must share an understanding of the time evolution of the state. That limits their choices of operations. It limits their freedom to operate. And as I said earlier, they must also operate on the same list of states. Finally, starting to see nodding in the audience. I think we're starting to get there. Okay. I can think of 5 ways to get there. I'm going to go through this very, very quickly so that we can have a few minutes for questions here. One way is to re-centralize the set of operations. The second way is by specification. Third would be by contract. Fourth, and the fourth and fifth one, the difference you got to kind of pay attention to catch here. Distributed computation based on local monitoring. So we're going to monitor only nearest to neighbor, and then on top of that, we're just going to exchange ideas about what we think is what is going on. Or true multi-stage monitoring where we actually do perform tomography on every step of the way, over every possible distance in the entire set of things. Generally, when I talk to experimentalists and I present this, I find that what's in their head is actually re-centralization. So we take those distributed control nodes and we just combine them into a single node. And that single node controls every single operation that goes on. Tells everybody whether you're going to purify or whether you're going to do entanglement swapping or the like. Simplest possible architecture. It's not going to work at 10 microseconds per kilometer round trip time for large distances. It's simply not feasible. We could treat every link exactly the same. This is in effect the way the network we are all using right at this very moment works. In terms of noise operators and everything else. What would be the quantum equivalent of the physical layer in this wireless network in this room that we're using? What would be the equivalent of that set of specifications? And in particular, we would find that this is not going to allow us to deploy links that are substantially different in any sort of physical sense. And the set of the set of behaviors we know depends not only on the technology but also on the distance and the quality of the fiber and whether or not there are splices in the fiber and everything else. It would limit our ability to do that. Let's see. So by contract would be sort of similar to specification except that it's decided on a per connection basis. I'm not going to go through with this because we are running a little short on time here. And the local monitoring, as I said, it might include information such as exchanging information such as I kept this bell pair in a memory of this particular type for this many microseconds. And that might, then the other guy can use that to calculate what the fidelity of the output state is. There are a few more slides, but let me go ahead and skip to the conclusions here on this. In order to actually pull all of this off, you're going to actually you must have the ability to assess the end-to-end fidelity of the states quickly. This problem has been giving us a headache in the process of actually implementing simulations for a year now. And there are trade-offs in the complexity versus the performance of the total operation. And there are some additional problems that we didn't talk about, including how you define what the 0 point is in time for various operations, which turns out to be interesting. And how to integrate it with other types of operations as well. Fundamentally, out of those 5 possible solutions that I have proposed, none of them really seem very appealing. The latter 2 in particular, you wind up consuming a tremendous amount of your operational time to actually perform tomography and monitor the overall set of the state. Finally, an advertisement. Just recently we held the first workshop on quantum repeaters and networks. I was part of the organizing committee for that. The second one will be in Europe in 2017. Rob Thew from Gisan's group, Geneva, is going to be the general chair for it next time. And this is my group of people. This figure is actually a little bit old, this picture is. But us having some fun. And finally, let's not all forget, we are now at about 90 hours out from Pluto. So in case you need a little bit of perspective, right? The New Horizons probe headed for Pluto is moving at 31,000 miles per hour. And it's about 3 million miles out from Pluto right now, and on Monday or Tuesday we'll be getting some fantastic pictures. That's real time. That's real time. That's 4.5 hours of one-way latency, too. Yeah. Any questions? We are at 40 right now, so Krista will have to take charge and chop this off wherever she feels necessary.
So you're trying to build a communication system that communicates,
Yeah.
quantum things.
Right.
And you have a communication problem implementing your communication system.
What a surprise is what you're trying to say?
Well, what I'm saying is, you've got means for teleportation all over the place. In fact, it's the whole point. So can't you come up with some way to bootstrap the whole thing? Sort of say, well, I need to communicate better information about my density function, my density matrix. So I have this ability to communicate. It's imperfect, but...
Well, even to make teleportation work, you need the supporting classical information to catch up to it.
Oh, that's true. Yeah, that's true.
And in fact, teleportation, the entanglement swapping itself is in effect a form of teleportation.
Right.
But of course, one of the big things you want to do is, once you've created the end-to-end entanglement, a use for it is to teleport data back and forth.
Yeah, anyway, I think you get my point. There ought to be some way to improve the estimate of the density matrix iteratively using the same machinery you're trying to.
In the words of the great Robert Heinlein, there ain't no such thing as a free lunch.
I understand.
Right? Any other? Yeah. Yep,
We
ton
take
stuff.
one or two more questions.
Let's see, who's up next? Barry, are you up
In the
next?
meantime, Barry could come
You want to
set
come
up.
and get hooked up?
Any others? Nathan?
So one of the things that I think is interesting about this problem is that there's a natural exploration-exploitation trade-off in that as soon as you set up a network between untrusted people, you can spend time either calibrating the devices or you can spend time trying to communicate. So it seems like a near bottomless problem in terms of you can focus a lot on device characterization and reference frame sharing, or you could spend a lot of time on trying to optimize your protocol. Have you thought about what's the simplest approach you can take that's actually meaningful and analyze that?
I think that's what we're trying to do. And in a couple of the slides I skipped over right there at the end, there's some very, very rough back-of-the-envelope estimates for how much time you would wind up spending doing tomography in the different schemes that I proposed. When I've talked about doing the distributed computation, which I favored for a while when we first started working on this, I talked to some people and they were just going, no, you can't do that. Right? The complexity of dealing with that computation is just going to be beyond anything you can imagine. There's no way to make it really work. So we shifted directions and we said, well, we're going to have to do the end-to-end monitoring then. We're going to have to do end-to-end tomography. If you do that, you're going to wind up spending a tremendous fraction of your end-to-end bandwidth on the tomography itself to figure out whether or not you're actually building states you can actually use. It's a substantial trade-off, and we don't have it's going to be, to a certain extent, parameter dependent, of course, but we don't yet have an answer to that. That's what we're trying to get to with this. Any luck?
You have to keep answering questions.
I can keep answering questions.
One
Any
more
other
question.
questions?
Oh, I'm sorry.
Thought you were talking to me.
No, I got
Yeah.
a question.
All right, let's see. All right, Martin's got a question. Can I have the mic? Aha, there we are. Do you want to cut it off, or do you want to let Martin ask his question?
Okay, one more.
I'm curious, do you envision to use the network for point-to-point mainly, or do you envision a scenario like in classical optics, OFDM, where you can have a frequency encoding, many participants communicating the network, the same fiber, but addressing different frequencies? Do you have these?
Are you asking whether an individual link could be multi-drop?
Yes.
It could be. All of the models of everything we have looked at so far all assume two parties in the actual on each individual link. But some of the things that Kai Nemoto and Bill Monroe did with the QBus stuff, it was actually sort of a multi-drop protocol. It could be done.
It could be crosstalk then, right?
Yeah, could be. I think you're on. Krista, anything else? Oh, so